All right, on number one, a bacteria population grows by 25% every hour. So if we are increasing by 25%, that means we need to take the previous 100% and add 25% to it. So thinking about that as a growth factor, I would say that my growth factor to model this situation would be 1.25. Okay? Now, Part A asks for the growth factor for half of an hour. 1.25 was the growth factor for a full hour. So the growth factor for half of an hour would just be 1.25 raised to the 1/2 power. Then for part B, to actually find the full population after half an hour, I would take my initial population of 204 and multiply that by my growth factor for half an hour, 1.25 to the 1/2 power. And then we can put that into the calculator. And since we're talking about a population, I would just round that to the nearest whole number. So 204 times 1.25 to the 1/2 power gets me about 228. All right, on number two, we have a function p representing the population of a city x years after 2020. So x, my exponent, is in years. Now, just by looking at this function, this part A is asking what is the initial population, right? January 2020 is when we are starting. Well, just by looking at the function right here, I see the initial population was 13,250. Now, after 1 year, well, all I need to do is plug 1 in for x. So I just need to do 13,250 times 1.025. All right, so my population after a year would be 13,581. And again, we're talking about population, people, so we're going to round to the nearest whole number. Now, C, D, and E just ask for growth factors, not a whole population. So, per month, well, if this growth factor, 1.025, is in years, if I want to convert that to months, I need to raise that to the 1/12 power, because there are 12 months in a year. So if I'm converting something from years to months, I would raise that to the 1/12 power. Now, if we put this in the calculator, we're going to get a not so nice looking decimal. So I'm just going to leave this as my exact answer, 1.025 to the 1/12 power. The growth factor per year then, well, is just this 1.025. Right? We're told that that is the growth factor per year. I don't need to raise that to any power at all. For E then, the growth factor per week, well, there are 52 weeks in a year, so I would raise this to the 1/52 power. Now, does this function represent growth or decay, and how do we know? Well, to determine that, we want to look at the growth factor. In this case, the growth factor is greater than 1, therefore, this represents growth. We are increasing. All right, so I'll say the growth factor of 1.025 is greater than 1. Therefore, this represents exponential growth. Okay? On number 3, all we have to do here is write a function to model this situation. So, an insect population was first measured at 432. 10 days later, the population has tripled. So, there's my growth factor right there. Okay, tripled tells me that my growth factor will be 3, but that is over a 10-day interval. we want to write a function that describes the insect population just d days after the population was first measured. So d is the variable. So I'll say my function is f of d equals, and we're told our starting value is 432. And my growth factor over a 10-day period is 3. So if I want to convert that to a 1-day period, my exponent should just be d over 10. Okay? Now we could, another way of writing this would be 432 times 3 to the 1/10 power to the d power. That would be another acceptable way to write it. So either way here, these are equivalent statements here. So either way of these, or either way of writing this is fine. On number 4, the value of a sports card grows exponentially, and we've got 2 points that might be kind of tough to see them on your paper, but the coordinate points that we know are 0, 7, and 5, 14. So this is a problem where, it might make sense to put those values on a table. That's kind of how we've talked about doing a lot of problems like this. So my first goal is to write a function to model this situation. Well, if I look at my table here, I can get my growth factor over an interval of 5. So to do that, I would just divide, right, a value by the previous value. So 14 divided by 7 is 2. But that is over an interval of 5, right? That's my growth factor. I'll abbreviate growth factor over an interval of 5. So to convert that to an interval of 1, I need to take this value and raise it to the 1/5 power. So that is my growth factor over an interval of 1. So to write my function then, I can say, it tells us to use s for our function and t for our variable. So I'll write this as s of t equals the starting value. So the starting value is 7. That's my y-intercept. That's the y value when x is 0. So 7 times, and we just determined that the growth factor for every 1 year would be 2 to the 1/5 power, and then to the t power. So there's my function that represents this situation. And then if I want to figure out the value of the card 2 years after purchase, well, all I have to do is plug 2 in for t here. So I can say s of 2 equals 7 times 2 to the 1/5 power to the 2nd power. And if I put that into my calculator, like that, we get, we're talking about money now, so if I round this to the nearest cent, about $9.24. And we can, if we look at the graph, right, after 2 years, right, that looks like that's about the right value, just a little bit less than $10. Number 5 is a half-life problem. So on this one, we know a sample of this element, vanadium-48, has an initial weight of 4 milligrams and a half-life of about 16 years. So, right here, we are given the initial or the starting amount, and then here, this tells me the growth factor, right? If I'm talking about a half-life, I know that my growth factor is going to be 1/2. So for part A, to write the function that models this situation, they tell us to use t for our variable. So f of t equals my starting amount of 4 times my growth factor of 1/2 raised to the t over 16 power. Right? Now, again, another way of writing that would be 4 times 1/2 to the 1/16 power to the t power. I kind of prefer the first way here, I think it looks a little bit cleaner, but the second method would still technically be correct. So then for part B, all I need to do is plug 16, 8, and 1 in for t into this function, right? So I can do f of 16. That would just be 4 times 1/2 to the 16 over 16 power. Now for this one, 16 over 16 is just 1. So this is 1/2 to the first power, which is just 1/2. 4 times 1/2 is 2. And that hopefully makes sense in the context of this problem, right? 16 years would be 1 full half-life of this element. So after 16 years, we should have half of what we started with. Half of 4 is 2. But then for my other two values, we may have to use a calculator for that. So I'll have 4 times 1/2 to the 8 over 16 power. And then I will have over here, if I plug 1 in, 4 times 1/2 to the 1 over 16 power. Right? And I can just plug both of those into my calculator. So 4 times 1/2 to the 8 over 16 power, if I round to 2 decimal places, is about 2.83. And then for this one, if I do 4 times 1/2 to the 1 over 16 power, we get about 3.83. All right, on number 6, we're looking at 2 different elements, okay, or 2 different substances. For this first substance, we know that we are starting with 100 grams at year 0, and then after 3 years, we are down to 50 grams. So for this first one, we just want to fill in the amount that we have left at 1 year, 2 years, 4 years, 5 years, and 6 years. So first, let's try to write a function to model this situation, right? So what I know is that after 3 years, my growth factor would be, well, I would just do a value divided by the previous value. So 50 divided by 100, that would just be 1/2 or 0.5. But if that is over a 3-year period, that means that my growth factor should be to the 1/3 power to get this for every 1 year. My initial value is 100. So this is how I can write that function, right? My starting value times my growth factor per year. And I got that by saying, well, my growth factor over a 3-year period was 0.5. So my growth factor over a 1-year period would be 0.5 to the 1 over 3 power, and then to the t power. So then I'm just plugging each of these values in for t, right? So for this first one, 100 times 0.5 to the 1/3 to the first power, then 100 times 0.5 to the 1/3 to the second power, and so on, right? I'm just doing that for every single one of these, just plugging in 1, 2, 4, 5, and 6. All right, so if I plug each of those into the calculator, for this first one, I think we should get about 79.37. For this one, if we plug that in, about 63.0. For this one, about 39.69. For this one, about 31.50. And this one, exactly 25, because that would be another 3-year period. So if my growth factor is 0.5 over a 3-year period, right, that should get me to exactly half of 50. Now, for part B, we're given another function, right, to model a different substance. 125 times 1/2 to the t over 4 power, where t is the years since the first measurement. So we have two questions, right? Which of these substances had a larger initial value, and which substance is decreasing more quickly? So to answer the first question, which of these substances had a larger value? Well, I know that my initial value for A was 100, and my initial value for B is 125. So B has a larger initial value, right? Because I know that it's 125. So actually, let me just type this. So B has a larger initial value. I'll just say 125 is greater than 100. Now, for the second question, which substance is decreasing more quickly? Well, for this first one, we determined that its half-life was every 3 years. And for this one, by looking at the function, I can see that its half-life is every 4 years. So we are decreasing more quickly if it is cut in half in a shorter amount of time. That means substance A is decreasing more quickly, right? So I'll say it like this. Substance A is decreasing quicker because it has a shorter half-life. And again, I'll give those values. I'll say 3, half-life of 3 is less than a half-life of 4. On number 7, we are given a graph and asked a few questions about this graph. So the graph represents the amount of medicine left in a patient's body so many hours after this medicine was injected. Now, by what factor did the medicine decrease in the first hour and a half? Well, those are the 2 points that we're given, right? We're given the initial value, and then we are given the amount left in the system 1.5 hours later. So to get that factor over that 1.5 hour period, all I'm doing is taking a value and dividing by the previous value. So 90 divided by 265, if we put that into the calculator, we get, if we round that to 2 decimal places, we can say 0.34. All right, so we'll say that that's about 0.34. Now, we can just leave this as a fraction too. I could just leave this as 90 over 265. But now, to figure out what factor the medicine decreased in the first hour, well, to do this, I can say, well, if I take this growth, this is my growth factor over a 1.5 hour period. If I want to convert that to a 1 hour period, I can just take this 0.34, or if I'll take the whole fraction, so I have the exact value, 90 over 265, to the 1 over that interval, 1 over 1.5. And if I put that into the calculator, so I can just take this value and raise it to the 1 divided by 1.5 power. There is my growth factor over each hour period. So 487 if we go out to 3 decimal places. But again, since that's an ugly number, I can just leave that like this, right? I don't have to put it in as a decimal. I can just leave it as 90 over 265 to the 1 over 1.5 power. Now, if I wanted the first 15 minutes, there's a couple of ways that we could think about this. All right, so I could say, well, my 1.5 hour time period in terms of hours, or I'm sorry, in terms of minutes, is 90 minutes, right? I could say that I want 15 minutes out of those 90 minutes. Or we could actually take this, which was, about 0.487, and I could take 0.487 and raise it to the 15 over 60 power, right? Either way, we should get the same answer. But if I do that, if I do 90 divided by 265 and raise that to the 15 divided by 90 power, again, because my time interval here is 1.5 hours, so that's where I get the 90 minutes. I get about 0.835, so that would be my growth factor over a 15-minute time period. But again, we can just leave it as this. We don't even have to put it in the calculator, right? We can just leave it as this fraction to the power. Now, for part C, our goal is to write our function per hour. Well, here, this was our growth factor per hour, right? So I can say, well, my starting value is 265. Now, I guess I should mention they tell us to use m for the function and then h for our variable to represent hours. So that's why my function is m of h here, equals my starting value of 265 times my growth factor. Now, again, I can either put it in as the fraction here or the decimal. I'll go ahead and put it in as the fraction just to be precise. So 90 over 265 to the 1 over 1.5 power. So that's my growth factor for the hour, and then raised to the variable power. In this case, again, they wanted us to use h for the variable.